So ocean water is in constant motion. None of it is actually staying still. And what we call a current is a large-scale continuous movement of the seawater. They're driven by several things that we're going to look at. And then here is an illustration of like the size and motion of some of the currents off of a coast. So they're not like a continuous stream that kind of branch out almost like a river within the ocean. So one of these drivers of how water is moving is called the Coriolis effect. This is something I'll post a second video about this to show what it is. It's based on the rotation of the Earth. So as the Earth turns, liquids on top of the Earth and gases don't actually move along with the solid like landforms of Earth. So because of that, movement on the Earth's surface rarely happens in a straight path. Because if you were going to be moving on the surface, because you are not locked into place like a solid, anything that's on water or in the air is going to stay in that actual place, and the Earth is going to rotate underneath it. So if you feel like you're going in a straight line, what is actually going to be happening in relation to the Earth is that it looks like you're kind of being dragged backwards because the Earth is turning this way. So it's easier by looking from the North Pole to see this. So if you're on the North Pole and launching straight down, if your target was here at 0 degrees east and west along the prime meridian, what would happen as you go, as time is passing, as you're moving, the path would actually turn backwards, not because you are turning, but because the Earth is turning against this. So how it looks, because we're on Earth and that is our field of view for things, that is going to look like everything is like a slight pull towards the west, like a slight drag this way. So this means in the northern hemisphere, it's going to go, everything's going to bend a little to the right, and in the southern hemisphere, it's going to bend to the left. This is a slight pull. It only affects things covering a long distance. There's a myth about this, about how in the northern hemisphere, if you flush the toilet, that it goes clockwise, and then in the southern hemisphere that it goes counterclockwise. So it's not true at that scale, but it is true that the ocean waters around Australia or in the southern hemisphere do turn counterclockwise, whereas ours turn clockwise. So like I said, northern hemisphere, it bends to the right, southern hemisphere bends to the left. So basically what we'll see with these major ocean currents from this, and we'll see it at the end when we see them all together, is that if you're in the northern hemisphere, things are going to tend to circle this way in a clockwise pattern. There are major currents that follow this general path. And then in the southern hemisphere, they're going to follow this general path towards the left or counterclockwise as they spin through. The second thing that is going to move the ocean currents is the wind. So as wind pushes along the surface of the ocean, it's going to move water. Wind is created by heat from the sun. So what happens is that air heated from the sun rises. So the air closest to the Earth, where it's radiating up and reflecting the sun's heat, is going to rise because it gets warmer. The higher it rises, the more it cools because it's further away from Earth's surface and it loses its heat into the atmosphere. So that air will then sink back down and the process repeats. As it gets closer to the Earth, it warms back up, rises, and goes back down. So it creates these wind patterns. They're in 6 what we call wind fields around the Earth. But basically they are just loops of air that is heating at our surface, rising up, cooling, falling back down, and going. And they pretty much fit in those latitudes that we talked about for our temperature ranges and our climate zones. So in the tropics, they're all pointing towards the equator, and you can see that they also follow the Coriolis effect, that they're dragging backwards. They don't go straight up and down. They're kind of dragging to the west. And then it's going to be the opposite here in the temperate zone, and then up again in the polar or the frigid zones. So you do not need to memorize these fields. You may have heard of some of these, maybe in history books, the westerlies and the trade winds. So this is when people were sailing across the sea before we used like tankers and things to do shipping. Explorers or shipping routes were based on these wind patterns. So coming from Europe, they would take the trade winds over, and then to come back, they would go up on the westerlies. So if you ever hear that, like in literature, in history books, they are talking about these wind patterns. So what that does is this will create a surface current. So as wind blows along the surface of the ocean, that air is going to push on the top layer of water, and it's going to drag some of the water along with it. And the way it happens is not as straightforward as it seems like it should be. So the wind travels this way. It would seem that the water should drag in the same direction, but actually what happens is there is a curve, like a 45-degree angle between the direction that the wind travels and then the way that the water travels along with it due to some drag, friction with the water being kind of stuck to the water beneath it. So it gets pulled a little bit off to the side. And then the water below that, so the surface current is going to pull on the water below it, but again at another 45-degree angle. And this is going to continue on and on and on. So if you look down, this just looks at about the top 100 meters. After that, there's really not enough pull from the wind to actually affect the water. So this wind surface current is called that, obviously, because it's at the surface of the ocean. It's only going to be the top 100 meters of the water. So overall, if you were to add up both the direction of the water currents and like the amount of water that moves in this direction, so that top current is going to be the strongest, the fastest, and that's going to slow down as it gets lower and change direction. So if you add those all together do some calculus to figure out this whole problem, the net water transport, the net effect of wind, is that it is going to actually push the water 90 degrees to the right of the direction that the wind goes. Which seems impossible, but this is why it works. It seems strange that it would push this way and cause a water transport this other direction. If you've taken other classes in physics or physical science, we talk about this. It's very similar to how electricity and magnetism kind of play off of each other, that one pushes this way and it creates this effect kind of in a circling direction around it or off in a 90-degree angle. But that's what you really need to know. The net water transport is important. So just because wind goes in one direction does not mean that water will go along with it. It's going to go 90 degrees away from that. And this is called Ekman transport, or the Ekman spiral. This is called the Ekman spiral because it was discovered by a man named Ekman. Okay, so as we put these together, what I was talking about before, those loops of the major currents, what we call them are gyres. So our Coriolis effect added to our surface currents creates these current like loops that we call gyres. You'll see this word a lot. I think we already talked about it in terms of the Great Pacific Garbage Patch on that first week of class. And these are just major loops of currents that tend to form within our ocean basins. So there are 5 major ones here, and then Antarctica, the Southern Ocean, has one just going straight across, like water just circles around Antarctica. We are on the North Pacific Gyre. So if we look at this, it tells you whether the water is warm or cold, and we'll get to that in the next slides, and what direction they're pointing in. You can see it follows that Coriolis effect. In the northern hemisphere, they're all going clockwise. Southern hemisphere, they go counterclockwise. But where they meet in the middle, they're going in the same direction. So along the equator, water is always being dragged to the west, okay, no matter what basin you're in. So this can have a lot of effects that we'll look at later on this week in terms of pollution, in terms of travel, in terms of everything about how the world works, migration patterns, everything in the ocean is connected to these gyres. And part of that driving force, and I'm going to go back for a second, for these hot and cold currents, or warm and cold, and again, these are relative warm and cold. It's kind of like with geologic age when we say something is young, but it's really millions of years old. We say it's warm, it's still cold, it's still the ocean, but compared to the colder version, it's going to be relatively warm. So this is going to matter for the physics and chemistry of how this works. So what is the bigger driver of ocean currents rather than just wind? Wind is not strong enough to actually cycle all this heavy water in our oceans over thousands and thousands of miles. It's called thermohaline circulation. So circulation just means to be moving within like a circular or like looped path. Thermo means temperature, like thermometer. Haline means salt in Latin. I don't know, a term that also use that, but haline is the same as saline or salty. So this is circulation that's driven by the temperature and salinity, the amount of salt within the ocean, because those two things are what determine the density of water. So the colder water is, the more dense it's going to get, and the more saline it gets, the more salt you have in it, the denser it gets. This is an experiment that we will try together. I will post the materials for it if you want to try it along with me. This is a lab that we usually do at school where you can actually separate water by density, that it won't actually mix unless you force it to, if part of it is fresh water and part of it is very, very salty water. So the drivers for this. Temperature and salinity changes. This is only going to matter for the top 1,000 meters of the ocean. So we're still kind of talking about the surface, where this actually changes before it just gets cold and salty. So wind currents are driven in the top 100, and then 1,000 is going to be thermohaline. The temperature is going to vary by location, so it's going to follow those climate zones that we looked at last week, where the frigid zone is going to be the coldest, the temperate is moderately, and then the tropics are going, or the torrid zone, whatever you want to call that one, around the equator is going to be the hottest. Salinity is a little bit harder to track. It's not just 3 like given zones based on geography, but it is somewhat predictable, more complicated but still predictable. So things that are going to affect the salinity or the amount of salt in ocean water, because it's not totally the same throughout, one of them is precipitation or rain. So the more rain or sleet or snow is going to add more fresh water and lower your salinity. The same with coastal runoff. So coastal runoff from streams, from rivers, from anything, even just, again, precipitation, but then not over the ocean, that runs onto the coast and then runs off through the beaches. That's going to lower the salinity because it's going to be mostly fresh water. And then things that could raise the salinity are going to be evaporation and freezing. So when water evaporates, it's only the water that actually evaporates out of the ocean and it leaves the salt behind. You've probably seen this if you leave like a glass of something that has sugar in it or salt and then you were to let it like evaporate out, you would see the crystals of the salt or sugar reform in the cup. You can try that one out. It'll take a couple weeks though. And then also freezing. So when salt water freezes to form like, not to form an iceberg, but if it were to form like at the North Pole, when that water freezes in the winter, the ice is only made out of pure water with some impurities in it, but the salt does not actually freeze into the ice cubes. So the salt is left behind, and the water in that like polar ocean is going to be a lot more saline or a lot saltier than water without the salt taken, or without the ice taken out of it, if that makes sense. So these first two lower the salinity. This is going to be low salt. These two are going to be high salt. So these are going to happen at places that have more extreme temperatures. So places like the Dead Sea, which is very, very salty. That's why it's so dense and you can just like lay on it. It has high evaporation because of the heat. And then around the North Pole has high salinity because it's freezing out all the salt or the fresh water. Okay, and so what happens at the end to bring this all together is that we end up with this thing called the Great Ocean Conveyor. So this has part to do with the gyres and part to do with the thermohaline cycling. It drives this big major current that goes throughout the entire ocean. So what happens here, the red is water flowing along the surface of the ocean, and then the blue is everything that is subsurface or down at that 1,000-meter level below the ocean surface. So what happens here is these are the places where the water warms up. It's low salinity because of high precipitation and runoff. So this warm, less salty water is pushed through, and then at these points we can see these are areas where it sinks, is where it's going to become more dense and more saline. So it's a place where the water is going to be taken out because it freezes here. It's going to cool down and sink to the bottom, make it all the way back through here. In the Indian Ocean, it rises up again. It warms back up as it gets to the equator and comes back here. The other half is going to continue along that gyre we saw before that around Antarctica. It's going to stay cold, come all the way up through the Pacific, and then heat up. So I'm not going to need you to memorize this path. All I need you to see is that this path is going to connect the entire ocean. So water from any point of the ocean will circulate the globe. Statistically, theoretically, every molecule of ocean water can reach any other place in the ocean through this ocean conveyor belt. So this is going to be important to us. We'll just go through some of these points. So water's flowing through the deep and shallow waters. This circulation is pretty slow. It takes about 4,000 years, but it does cycle through. So in terms of everything else we've talked about, the ocean age, that the oceans are like 200 million years old is the ocean floor age. This is still very quick, but in terms of our time periods, it's very slow. It's very important for several reasons. This allows life to exist throughout the ocean. Without this ocean conveyor belt going, everything would die, because this is the only way we get oxygen to the deep water. So photosynthesis is happening at the top of the ocean, and then as the water cools and sinks, the oxygen in that water is brought to the lower areas of the ocean, and it brings nutrients from the lower ocean where things have fallen and decomposed and kind of rotted away into their elemental nutrients. It brings that back up to feed the plankton and other algae at the top of the ocean. So it's kind of like it brings fertilizer and then oxygen comes back down. So it's the same type of cycle as we talked about when we talked about photosynthesis and cellular respiration. back in freshman biology where animals need plants, plants need animals. It's that same type of concept. So life at the top brings oxygen to life at the bottom, and life at the bottom brings nutrients up to life at the top. This path also shifts, so when this path shifts, it causes changes in weather patterns. The ocean air, the ocean microclimates, I'm not sure how to characterize them here, have an effect back and forth with air temperature and the way things happen. So we see that like with tropical storms and hurricanes a lot, that what's happening in the ocean matters. But it also can just change like rain patterns, smaller storms. It doesn't always have to be a hurricane. It can be just whether it's a drought or not, couldn't be based on shifts in this ocean conveyor belt. So these are natural shifts. So this is a general thing. Sometimes it's lower, sometimes it's higher, sometimes it's slower or faster. But it does have an effect on our lives. The most famous one, and something we used to talk about a lot, is El Nino. So the El Nino effect is based on the ocean currents and then the effect that they have on our weather in North America, maybe in South America too. So what happens in an El Nino year is certain areas of the country, because of the change in currents and wind patterns, it leads to a backflow of warm water to the west coast of South America, which leads to warmer temperatures, larger storms, and more precipitation in the whole Western Hemisphere. So it leads to like wet and cool. Here it's basically just bigger storms that will happen. It's led to like bigger storms here. This was a thing that during that last huge drought that we had in California, we were hoping for an El Nino year to bring more rain, and it wasn't as big as we thought it would be. There was an El Nino event in, I want to say it was 98 or 99, that in the Midwest, we got storms that we got like 6 feet of snow in 2 or 3 days there. So it can cause like huge storms and flooding as well. But it's all based on the ocean currents there. Some other effects of the currents, or things that we're going to look at. One of these is just an interesting way that they studied the currents. It's called the Friendly Floaties incident, I guess we should call it. Basically, in 1992, a shipping container that was going from China to the United States on a boat fell off into the Pacific Ocean and broke open. And this wouldn't have amounted to anything except that it was filled with nearly 30,000 like rubber ducks. So they were bath toys. I forgot what they were, like rubber ducks. There were 4 different little toys that were in there, but basically floating water toys. So instead of just sinking into the ocean and being more pollution, they floated around the ocean for years. And because we knew, like they acted the same way that pollutants do, that trash did, but because it was very specific and identifiable, it was easy to see where it came from and then use that to track where the water was flowing and how fast it got there. So we can see here. Here is the incident. It was like right in the middle of the Pacific Ocean is where this container fell off the boat. And then all of these places are places where they found them washed up on shore later on. So based on these findings and when they were finding them, so they were finding them like 10 years later, 15 years later in Europe, they could track like how many of them got there, so how strong the current was to certain locations, and how long it took for them to get there. So these may still be floating around out there somewhere. The plastic may have degraded at this point, but this was just kind of illustrative of what we're going to talk about next about pollution and how it spreads. The second thing we're going to look at is the Gulf Stream. So this is something you've probably heard about before. When we're talking about it in the air, there's the jet stream, which is what fuels the Gulf Stream here. So this is the fastest current in the world, the fastest ocean current. It's very strong. This is used for a lot of travel or shipping. So it's the fastest way to get from North America to Europe is along the Gulf Stream. And you can see that it's driven by this hot water in the Caribbean. So if we look at this heat map over to the right, because the Caribbean is so shallow and close to the equator, like on the equator, it's all in the tropics, it heats up very quickly. So it's a small amount of water that's very close to the surface. So based on that, it's going to drive a very strong thermohaline circulation here. So this goes up the coast of the United States, past Florida, up, and it goes all the way over to Europe. And this has a lot of different impacts, like I said, for travel, for maybe it was just travel and shipping. This is part of, I know somebody talked about the Bermuda Triangle before. This is going to fall into that type of mythology of why it's there. It can lead to some issues when people are not used to such a strong current. Another thing it does though, so in terms of climate or ecology, so this is warm water, we've said all this stuff, is that it raises the temperature of the entire Western Europe by several degrees Celsius. So this terrible map is here. Sorry, it's so grainy. But what happens here is this water is going to travel all the way up, and it gets up to here, and this line that it's drawn through goes through London, just because London is like a known city. So if you think of London, it's very similar to like New York, climate-wise, that it's pretty temperate. Yeah, it's not like, you don't think of it as this very cold place. But if you draw a line at that latitude that London is through and see what other cities are located and what areas are located in that area, they're all places that we consider pretty cold. So here, Western Europe is at the same place as Canada, as Siberia over here, places that without this Gulf Stream bringing warm water and heating up this area, most of Europe would be, Western Europe would be like as cold as Canada instead of more like the weather down here. So it has big impacts on the climate. For our global climate change, it would affect, you know, if this were to stop moving, and this is something we'll talk about on Friday, more of like that currents are very strong, but they are not foolproof. They can be damaged by human activity. Another issue of that is that because this, like we use it to travel, we use the Gulf Stream and the jet stream to get places quickly and have the water or wind push us. It also means that anything else that gets into the Gulf Stream is also going to go. So like the friendly floaties, things like oil spills. So here, we're just showing the spread of oil spills. So there's a couple of famous ones in here. I know we talked about one very briefly that first week that just happened in Mauritius. But the Exxon Valdez oil spill that happened in, I want to say the 80s, maybe the early 90s. But before your time, this was this hugely famous oil spill. There was a tanker owned by Exxon, the gas company, that ran aground in Alaska, on the Alaskan coast. And if you know anything about Alaska, it's that we're very, or environmentalists are very protective of Alaska's landscapes. So all this oil spread out, you can see that it spread out over almost 500 miles of coast were affected by it within a few months. And so it caused devastation to the wildlife there, to the communities up there that rely on the ocean. So just because it landed in one spot, because of the currents, the oil is pushed out, and there's no way that we can stop it because these currents are so strong. The second one is something that, sorry, I was confident this was within your lifetime, but maybe it was not, was the Deepwater Horizon oil spill that happened in the Gulf Coast. So this was an offshore oil rig, so they were drilling for oil underneath the ocean surface, which is dangerous. There was a leak within the pipe, and the oil rig blew up. So it was devastating that people died, were injured by this. And then this pipe was just gushing oil into the ocean for months before they patched it. And the oil, because the Gulf Coast is close to the Gulf Stream, you can see right in here where it got sucked in to this ocean current. And the oil made it, oh, I didn't put it all the way over there, but it made it all the way to Europe. If you've ever seen pictures of what happened to the Gulf Coast, it was devastating. Everything was full of oil. The beaches were full of oil that had turned into goop. But that also made it all the way over to Europe, and they were having this pollution show up on their coasts as well. So because of currents, because something that happens in one place of the ocean never just stays there, it means, for better or worse, we have to be very careful about what we're doing in one place because it can spread. We will move on to more positive aspects of this. So we'll look at tomorrow. This is just the recap. Tomorrow you're going to be doing your other activity on island ecology, but let's push it to next week. So Friday we're going to do a mini lab. We will talk about the good things that come to this, animal migrations and things like that that are possible because of our ocean currents. So to recap, there was a lot of information here, but you need to know all oceans are connected. Cold water is denser than warm water, and the more solutes that dissolve in water, the denser it is. And these are the things that drive the currents of the ocean, is those facts about physics of water. And that is it for this. So make sure you go and answer your questions on this. And that's it for your assignment.